Hi everyone. I think all the lectures so far you've kind of seen my back as I've written on the board here. Today I'm going to talk to you and do very little writing. The sections that I want to talk about in the textbook are 9.7 and 9.8, which have to do with different kinds of called non-Euclidean geometries. Euclid was the fellow who lived back about 2,500 years ago. We gave his proof for the fact that there are an infinite number of primes a couple lessons ago. And one of the things he did, which was maybe the most remarkable, is he made a textbook which is used 2,500 years later, more or less. He basically looked all around and said, people have been building things, the pyramids, the Parthenon, houses, furniture, whatever, and they've been using geometry to do it. How do you use geometry? If you have two parallel lines, this angle is the same as this angle. If you have a square, then you have four right angles and you have all equal sides and things like that. And you can talk about the diagonals and all those kinds of things. So that's all geometry, and that's all used for building. And those things had been used for probably hundreds or thousands of years without anyone giving them any thought. And Euclid came around and said, how do we know that these things are true? How do we know that they're true? Just because they've always worked, how do we know they're going to work in the future? So what he did was he found them all. There are about 470 theorems of geometry. And he realized that you didn't have to just accept them all as being true. All you had to do was accept about 5 of them as being true. One of them said that between any 2 points, there's exactly one straight line. Another one said that once you have a line, there's just a unique way to extend it. You can't extend it 2 different ways. Yeah, that's obvious. Another one said that if you have a point and you have a distance for a radius, you make exactly one circle with this as the center and this as the length of the radius. Okay, yeah, that makes sense. A 4th one seems kind of obvious. It just says that all right angles are equal. Okay, you have 2 perpendicular lines, all those right angles are equal. And then the 5th one said, if you have a line and you have a point not on that line, then there is exactly one line which goes through this point which will never intersect this line. Okay? Those were his 5 foundational axioms, and using those he was able to prove all the rest of the theorems of geometry. And if you took a class in geometry in high school, say, then you basically did the same thing that Euclid taught back 2,500 years ago. What other book do you ever have that's 2,500 years old? If you read Shakespeare, that's a mere 500 years old. Okay, but Euclid was 2,500. Well, anyway, as I just mentioned those 5 theorems, this last one is the one that kind of bothered mathematicians. And it bothered them because these other 4 were so simple to state and simple to see that there was just no denying it. But this one was a little bit different. It's longer to state. It's talking about going on forever. Well, you can't go on forever if you're going to stay on the blackboard, on the chalkboard, on the whiteboard here. So how do you know for sure? So a whole lot of mathematicians thought, hey, you know, instead of using these 5 to prove all the other 465 or so of them, maybe we can do it just with these 4. And maybe these 4 can be used to prove all these, including this one. Maybe this one is a theorem along with all these others. Maybe this can be proved along with all these others. So they tried proving it for years and years, and they thought they had done it. And then, you know what? I have a whole video that talks about this. It's called Mathematics versus Truth, the Battle of the Titans. It's a PowerPoint. And so for anyone in my class, they're going to be seeing it. And if you're watching this right now, if you're a member of my class at Davenport, you're going to see it. If not, then you can write and ask me about it. But I'm not going to redo the whole thing up here. It's too long and it's too interesting to try to do a partial job on it. But basically, what they discovered is, first of all, that this is a needed theorem. And secondly, this was even more remarkable. Just like if you have a game, like a game of chess or a game of marbles or whatever, you can have one group of people that play by one set of rules over here, and you can have another group of people that play with another set of rules, and maybe these rules are somewhat different from these. But as long as they're self-consistent, as long as they don't contradict each other, this can be a completely good set, and this can be a completely good set. And for one group to say yours are wrong or yours are wrong, it really doesn't make any sense. They're both just the ones that they chose. And it turns out that geometry is kind of like that. You can have a theorem that says something different from what Euclid said. You can say, hey, given any straight line, there are no other lines. All other lines intersect this. There's no parallel lines at all. And it turns out that if you start with that as your 5 axioms, you just end up with a different game, a different geometry than the one you started with. And it turns out that if you have that set of rules instead, you get yourself the geometry of a globe. Because on a globe, straight lines are lines, they're called great circles. They're lines that if you just take a rubber band or a string or a cord, let's see what I've got here. This kitchen calculus. Here we go. Okay. I didn't think about this until just a second. But you take and you just stretch something along the globe and you stretch it tight. That thing, and I need 3 hands, 4 would even be better. And if you stretch it tight, that's a straight line. Just like if you stretch something tight along the board, that's a straight line on the board, okay? So a straight line on a globe, practice it. And it turns out that your equator is a straight line. It turns out that these longitudinal lines are straight, but the other latitude lines are not straight. Because if you try to put one here and put one there and you pull it straight, it doesn't stay on the latitude line, it moves up. And that's why if you are flying from, say, Grand Rapids, Michigan over to London, England, instead of staying right along the latitude line, you go way north. Let me get it up here. Instead of staying along the latitude line like this, you go way north. You go over Greenland, because that's the straight line. That's the shortest distance. So anyway, the point is, that's a non-Euclidean geometry, and it kind of revolutionized the world because it showed people that what they thought was the one and only truth was not the one and only truth at all. This was just one particular choice, and you could have other choices as well. Remember what we learned with base 10? Base 10, it turned out, with using 0 through 9, using 10 symbols, that was just a choice. It was just a convention. And by having other choices, you have base 2 or base 5. And those are all different choices which would work just as well as base 10. So it kind of revolutionized the way we thought about truth, because people thought about geometry as being maybe the one clear truth in the world. Immanuel Kant, the philosopher, talked about geometry and mathematics as being the obvious truth, the one that we know even before we're taught it. We know it innately. And it turns out that things are much richer and more mysterious than he realized or other people realized. So anyway, that's all I want to talk about that. There's all sorts of neat stuff. Another kind of interesting thing about geometry comes from taking a piece of paper, and I think you can see it here, just a strip of paper, and you take it and you just put it end to end. You make yourself a little cylinder like this. See this? And then you cut it in half. And here's what I mean by cutting it in half. You take a scissors, and as I say, you put it right down the middle, and you just cut away, and then you guess what's going to happen by the time I'm done cutting. And so here you see I've got it right there. I'm going to break it apart the last little bit, and probably as you expect, you get yourself 2 different little cylinders, each the same general shape as the first, but just half the width. And now the question is, what happens if I do one little small difference in this thing? Here's another similar piece of paper. Before I put this end to end, I'm going to put a twist in it. Just one twist, like this. and then I'll tape it together. And the question is, how does this make things different? And the strange thing is, it takes something which is two-sided and it makes it into one-sided. Here was the original one. Think of it this way. If you have an ant on the outside and you have a spider on the inside, and that spider can't crawl around over the edge, then there's no way that that spider is ever going to be able to crawl over the edge to get the ant. They live on two different sides, two different worlds. But here, this strip, it's named after a person by the name of Mobius. If you take this and use your finger and go all the way around and just keep using your finger like this spider, and you go all the way around, and by the time you get back again, now you're on the what you might call the underneath side, but there really isn't an underneath, it's all one side. And you keep on going far enough, and you end up right back where you began again. And if I had drawn a line, I would have had a line on over this whole thing, on quote both sides of it, okay? So if I were to pull it apart, this line would be on both sides of it if I were to untape it, okay? So it's one-sided, okay? And what happens now when I take this one-sided thing and cut it apart? What am I going to get? Can you picture it in your mind? What's amazing is that it's simple enough to do, but it's very hard to imagine what this is going to be. Okay, what am I going to get by the time I cut it right down the middle all the way? Most people guess I'm going to get two interlocking rings. The other two were not interlocking. I could pull them apart, but it turns out it's even more surprising than that. You still have just one ring by the time you're done. It has two twists in it rather than one this time. So that's a Mobius strip. Very interesting stuff. And by the way, that is why if you have a car with a belt in it, it's called a serpentine belt that runs your compressor and I don't know all the different things in your car that need to be run by the engine. Then they put a twist in it, just like the Mobius strip. Because that way, as it goes around, you're using both sides. Otherwise, it would be just the inside of it that would get worn away and the outside would be fine. But by putting a twist in it, now you can get basically twice the mileage out of it because now you can wear on both sides. How clever is that? So a very neat example of where you use geometry. And the last thing I want to say, and this is just all fun stuff, I've given hour-long talks on all this stuff, is something called chaos. Here is a book by James Gleick called Chaos Making a New Science. If you ever want to read a fascinating math book that reads like a novel, this would be the one. Every chapter is filled with human drama as these people discover this thing called chaos. And the easiest way I have to describe it is it comes off of a poem which I've heard it attributed to Ben Franklin. I don't know if him or someone else. But anyway, here's how it goes. I guess maybe I don't need that. For want of a nail, and this is a nail for a horseshoe, for want of a nail, a shoe was lost. In other words, there was a nail gone, and because of wanting a nail, you don't have a nail, the shoe gets loosened and comes off. For want of a nail, a shoe was lost. For want of the shoe, the horse was lost. For want of the horse, the rider was lost. For want of the rider, the battle was lost. For want of the battle, the kingdom was lost. Okay? So it's this idea that you can have something that happens that causes a totally different outcome than you would have imagined because of a tiny little difference. Here, this one horseshoe, one nail is forgotten, and that rider might have been influential in the battle, and that battle might have been influential in the war for the kingdom, and so everything hinges on this. It's very similar, if you've heard of the Continental Divide, it's the spot in the western United States where here you have the Pacific Ocean out on the west, and here you have the Atlantic Ocean far, far out on the east. And if you're up in the Rocky Mountains at just the right spot, and you stand there, it's called the Continental Divide, and you turn your head and spit in this direction, that little spit will get washed by the rain down this way, and will get caught into a river and might eventually go into the Missouri and then into the Mississippi and go off in the Gulf of Mexico and become part of the Atlantic Ocean. On the other hand, if you just turn your head, stay in the same spot, but turn your head and spit this way, now it gets washed down this side of the mountain, and it gets into the, I'm not sure which, maybe the Snake River or the Columbia, or the Colorado River, I guess, wherever, and end up in the, if it doesn't evaporate first, in the Pacific Ocean. So there's a case where one little tiny difference makes a whole difference in the outcome. There's a book entitled The Road Not Taken, which describes how if certain things in history had happened just a little bit differently. For example, Alexander the Great. There was one point where a guy just about killed him. And if he had been able to strike that second blow and kill Alexander the Great, then all of Alexander's conquests that brought that whole part of the world together would have gone by the wayside, and all the things that came from it, like Judaism, Christianity, and the Western culture that went up into Europe, and all that stuff would have been different. And literally, if that guy had gotten that second blow in, I wouldn't be standing here right now. You would not be doing whatever you're doing. We wouldn't even exist, okay? The whole world would be so different, we wouldn't even exist, just based on that one little thing, okay? That one little thing. So lots of examples. Right now in the world, we have the corona virus and the COVID-19 pandemic that's going on. That whole thing has happened because of apparently one virus that got from a bat into a human, and then it transmitted from that human to another, and the whole world has changed. The whole world has changed because of that one little thing that happened over in, I forgot the name of the town in China, some town you never even knew, and suddenly the whole world is different because of that. So that's an example of chaos, where you have totally different outcomes depending on the original. And that same sort of thing is used by computers to the same idea of chaos theory is by the way, I guess maybe I should mention this too. Along with chaos theory, you have what are called fractals. And a fractal is anything that just keeps reproducing itself as you magnify it. So for example, this could be the coastline of some continent right here. And now that's the map. And you take this map of that particular area that looks straight there, and you find a local map of it, and it's going to look like this again, same as that. And now you take a very local map of this little area that looks straight, and it's going to look like this again. And now you take a little portion of that looks straight, and you walk around it, and if you walk around it, you're going to find it's jagged again. And finally, for a place that looks nice and smooth for you, if you were a snail, you would be jagged again. So it keeps reproducing itself at more and more magnifications as you blow it up. Here's another example. How many miles of blood vessels do you have in your body? Do you know? It's about 20,000, as I've been told. Here's your aorta coming out of your heart, and then you have arteries that come off of that, and arteries that come off of that, and then come off of that. And finally, they become these tiny little capillaries, and then you have the same set of veins that bring it back to the heart. And by the time you add up all those little things, you got about 20,000 miles. And the point is, each one of these is like a little reproduction of the whole thing. Okay, so all sorts of examples of fractals in nature. Another one, by the way, I mentioned this in the video of just last time, or a couple times ago, having to do with scaling and geometry. But here's the inside of your small intestine, okay? And your small intestine is used in order to absorb all the food that you eat. All the stuff that you eat really doesn't get into your body until it gets into your small intestine and gets absorbed. It's really like on the inside of a pipe, and it's really not in the pipe yet. It's not in the pipe material, it's just on the inside of the pipe. And in order to get into the material of the pipe, here's what has to happen. So here's the inside of your small intestine, and there's these little finger-like things, which are called villi, and then on these little things are little smaller ones, which are called millivilli, I believe, and then on those there are even smaller ones called little microvilli. And that's basically to give your small intestine a whole lot of surface area, so that you just have a whole lot of surface area to absorb all of the nutrients that you eat into your body. And I've been told that if you take all those little villi and cut them and flatten them out and take the total area, you would have enough area inside your small intestine to cover a whole tennis court. What do you think of that? To cover a whole tennis court just with the things inside your small intestine. So that's all kind of new geometry. Mandelbrot was the new fella that just realized there's a whole lot of interesting geometries that we haven't thought about yet. And he has a famous saying. He said we've been told that trees are straight lines and that mountains are cones and trees are cylinders and things like that, and that rocks are spheres and so on. He goes, no. He says that's not the way nature is. Nature is all these things that are very, very they're fractals. They keep reproducing themselves more and more as you get down lower and lower and lower and such. So let me write that word down if you're interested. A lot of neat stuff there. And again, there's all sorts of practical use for this. It turns out that Hollywood is aware of it. Hollywood uses mathematics and these ideas of fractals to generate very realistic looking landscapes. Look at that. That's just a mathematical scene right there. Here's some other ones. Let's see. I think I've got. Look at there. Looks like someplace down in the desert southeast or southwest rather. But that's just a made-up scene. Okay, there's another one. Just totally a made-up scene. And so computers are being used to make video landscapes for. Oh, that's a cool one. For motion pictures. Isn't that cool? So anyway, there's a quick introduction of lots of called non-Euclidean geometries, things that are all having to do with space and distance and so on, but different from what Euclid originally taught us 2,500 years ago. So there you go. Very good.